light years away from us, for instance, at the edge of a black hole or inside an exploding star, this is actually not the case. Great mysteries of the universe actually surround us all the time. They even permeate us and sailing straight through our bodies. So cosmic rays are indeed messengers, or can be regarded as messengers from the broad universe, the universe at large scale, a reminder that we are part of it, and a reminder that there's still a great deal of mystery out there beyond what our eyes see and what can still be observed and detected. So what are cosmic rays actually? If I just give you a small picture as to show you what they are actually. They mostly consist of energetic protons, electrons, and at an altitude of approximately 35 kilometers above the Earth's surface, they start to interact with the atmospheric components, the atmospheric molecules, and a whole shower of secondary particles actually result of this interaction. And what we actually observe are protons, or maybe or mostly neutrons, at the surface of the Earth itself. So they travel at a speed, near the speed of light, extremely high energies in the GeV, giga electron volt, much more faster or strong than any particle accelerator on Earth can actually accelerate particles. So the strongest particle accelerators are actually located out in the universe and at millions of light years away from us. So the question arises, where do they come from? And also, how did they get accelerated to such high speeds? So the next question we can also ask is, why are cosmic rays actually important? They are very rare actually, or the density of them are actually very small. They're only 1 in a million exist in particles per million in the interstellar gas. But on the other hand, they have millions of times more energy than the normal interstellar gas. So their speeds are roughly around about 98% the speed of light, and energies in excess of 10 to the power 9 electron volt. They're actually several million light years young, so they originate at very far distances away from us for the most majority part of these cosmic rays. They are a direct sample of matter of interstellar space. They actually contain elements or molecules, elements that are much too rare to be actually seen in spectroscopic lines from other stars. So in that sense, they provide an important information about the chemical evolution of the universe. The possible origins of cosmic rays are actually the sun, our closest star. Then most importantly, I think the majority what we understand at the moment, they come from supernovae, pulsars, and also gamma ray bursts. So I will discuss each and every one of them in part as I proceed through the evening. First of all, supernovae. Well, we know supernovae are the result of massive star. When a massive star explodes, that is when a massive star comes at the end of its lifetime. Duration of these supernovae can be for several days. Similar or a very recent one, or a very popular or prominent one, is the Crab Nebula, shown here in this picture here below, indicated here, and also a blow-up picture of the central region of the Crab Nebula. It shows the remnant of a supernova that occurred 1000 in the year 1054. That's the time actually when the normal people start roaming over Europe. I think they didn't have any time to look up in the sky. They were just trying to plunder the civilizations of Central Europe at that time. So the Chinese were actually the first, or reported their observation of the Crab Nebula. They actually observed it in a daytime. So Pulsars are also nowadays very prominent. They are rapidly rotating neutron stars, as shown here in this view graph, with extremely strong magnetic fields. They rotate at several hundred times per second, and that is an ideal opportunity for particles to be accelerated to close to the speed of light. And that is where we think some of the origin of some of our cosmic rays that we observe on Earth. Then, of course, gamma ray bursts. We all know that they are the most violent events or results of violent events in the universe. Contrary to supernovae, they last for only a few seconds. They are extremely intense. They can be observed by space telescopes orbiting the Earth at tera-electron volt energies. As I said, the bursts last only for several seconds, and they occur quite randomly. It's shown here in this view graph in the middle. They were in the 2025. In 25, there were 2,704 gamma ray bursts observed throughout the universe. And they are thought to be the cause of sometimes collapsing massive stars, as shown here, 2 neutron stars. They merge together, and they are also a source of high energy particles. So the question is something relevant to discuss. What is the difference between particle and photon astrophysics? That is the two main regions of research nowadays. So our universe or the skies can actually be explored through photons, ranging from the radio astronomy part of the spectrum. In Southern Africa, we have the square kilometer array, microwaves in South America, in the Atacama Desert. We have microwave observatories. Optical observatories, I don't have to mention it too much. We all know about the South African Large Telescope, SALT, and then also gamma rays, the HESS telescope in Namibia, to the west of Namibia. And then, of course, the other branch of astronomy is actually particle astronomy. So today, as I said in my introduction, astronomers need to take into account multi-wavelength astronomy in order to form a complete picture of our understanding of the universe. Radio waves, as we know, that is at Hart Radio, the Karoo Array Telescope, SKA, the Square Kilometer Array, they rely on energies coming from rotation and vibrations of molecules, particularly the hydrogen molecule. So it's extremely low energies, very long wavelengths, shown here the wavelength in meters. Then we go to the SALT and SAO, that is the energy coming from electronic jumps in atoms. The spectral region is the optical or the visible wavelength region. And then we go to higher energies, gamma rays, X-rays, and that is where the HESS telescope comes in. And that comes from, or the origin of these photons that we observe come from nuclear transitions in the nucleus itself. So it's very high energies, and most of that can be covered by our instrumentation located in Southern Africa. Also, in terms of multi-wavelength astronomy, the particles, the solar wind coming from the sun, as I've discussed in a previous presentation to you, which is responsible for our disturbances in the Earth's magnetic field, space weather effects, ionospheric disturbances, the radiation belts, the Van Allen radiation belts, which is responsible for capturing high energy particles, which we sometimes see descending or in the South Atlantic anomaly region. And then also, of course, cosmic rays. So Victor Hess, if I can go back into history, on the 7th of August, 1912, he made his epic balloon flight, where he detected for the first time in mankind's history the existence of cosmic rays. And for that, he earned the Nobel Prize in 1936. So as far as my knowledge is concerned, he's not related to Rudolf Hess who lived many years after him, but so they are not related to each other. Actually, 100 years later, in August 2012, we had a conference commemorating the anniversary of 100 years of the detection and of cosmic rays by Victor Hess. That was done at the railway station at Bad Saarlau in Piskau, Germany. That is actually where Hess landed with his balloon after his epic voyage into the sky, a couple of kilometers high, where he discovered what they call in German the Höhenstrahlung, and if I can translate it directly, it is just the altitude radiation that was called, at that time. So what is the difference between photon and particle astronomy? We all know from photons or of visible spectrum astronomy, we can point your telescope into the direction where the photons are coming from. You know what is the origin of it, where it is coming from, how bright it is, and you can also even install a spectrometer and analyze the wavelengths, and in that sense you can actually detect the chemical composition of a star's atmosphere. However, in the case of particles, and in this case cosmic rays, you do not have such information because the whole of the universe is permeated by magnetic fields. And these particles from cosmic rays are charged particles, so they spiral along and being deflected by the interplanetary or magnetic field, and you don't have any information where they're coming from. So you can detect it in the South Pole, as shown here, but actually the source might be on the northern region. So in that sense, that is a huge difference between particle astronomy and photon astronomy. If you look at the cosmic ray composition that we know so far, we compare the blue, that is the graph that shows the solar system, what we detect in the solar system, and the red curve shows the galactic cosmic rays. So there are huge question marks or differences between the composition of the solar system and the galactic cosmic rays, particularly around elements such as lithium, beryllium, and boron, that is the light elements. We still don't understand why there is so few in the solar system, but so much coming from the galactic cosmic rays from outer space, that is from outside our Milky Way and coming from other sources in the universe. Then also, when you go to higher and heavier elements, scandium, vanadium, and manganese are also elements that we do not know why there's such a discrepancy between the solar system, and also the galactic cosmic rays. These are outstanding questions that we still don't know how to resolve, but the research is still going on. The cosmic ray spectrum on itself is also a very interesting phenomenon. On the y-axis, we have the number of particles, and on the x-axis, we have the energy as a function of energy. When we look at lower energy particles, we normally detect statistically 1 particle per square centimeter or per square meter every second. And these are mostly the particles that we detect with our neutron monitors. Those are the high flux particles. If we go to higher energies, we see here in the vicinity of 10 to the 15 electron volts, the particles is 1 per square meter per year. And then even further down, the most extreme energy particles of the cosmic ray spectrum is 1 particle per square kilometer per year. So they are extremely rare, but they do exist. Practical examples of shocks, that is what we believe is the propelling or the driving force for accelerating cosmic ray particles in the universe. We have nuclear explosions. That is, we don't see that nowadays, but these are practical examples of a nuclear explosion or nuclear test by some of the maybe France in the Bikini Islands, and that is a shock wave for accelerating particles. Then, if you sit at the coast and you look at the waves coming in, this is also a typical example of a shock wave where particles are, or waves are being accelerated with the force of the ocean, and that is what surfers use for having their fun in the waves of the ocean. That is a typical example. Another example of a shock wave, which we can find in practice or in everyday life, is a bullet that flies through the air, or a boat that moves through a piece of water with the bow shock and the shock wave in front of it. That is a typical example of a shock wave. And then you can test experimentally in your zinc the water flowing from a tap into your zinc. A shock wave is also very, very clear to be seen here. So you can test that, and that is something in everyday life. In our own solar system, for instance, solar flares, coronal mass ejections, they are typical and perfect examples of a shock wave leaving the sun, and then later on they impact on the Earth's magnetic field, forming a standing wave on the day side. And when this effect is quite dramatic, or on the certain circumstances, it can lead to disturbances in our near space environment and maybe affect our technology. But that is a talk for another day. Just an example of typical examples of shocks that we can experience in our everyday life. In terms of the heliosphere, it's also very interesting. This is a bubble, or the magnetic bubble, that surrounds our solar system coming from the sun, the effect of the sun's magnetic field, the accelerating of the particles. We estimate that it is around about 200 astronomical units in diameter. So the solar wind flying at a speed of approximately 400 kilometers per second, magnetic field, that confines our boundaries of the heliosphere. And there are two spacecraft launched in 1977, the Voyager 1 and the Voyager 2. They have the opportunity, or they had the opportunity, to travel through the bow shock several years later. And that can actually constitute humanity's furthest distance or journey ever traveled. Actually, on the 25th of August 2012, Voyager 1 actually crossed the boundary, or the region where the sun's, the heliosphere ends, and it entered into interplanetary or stellar space. And Voyager 2 followed later on, and that was in 2018 actually. I don't know whether it was sheer luck or just by coincidence, but on the 25th of August 2012, Voyager 1 crossed the heliosphere. And how did we know that? We had a particle detector, or a cosmic ray detector, on board of Voyager 1. And that was exactly 100 years and 18 days after the first observation or detection or discovery of cosmic rays by Rudolf Hess on the 7th of August, 1912. So by sheer luck and coincidence, that happened and commemorated the great discovery by Victor. Well, in terms of how do we observe the cosmic rays on the Earth's surface, there are several, or is a network of neutron monitors around the globe, 29 in total in the northern hemisphere and 11 in the southern hemisphere. In southern Africa, we have a neutron monitor at Tsumeb, Potchefstroom, Hermanus, and then also Sana'i, which is under the auspices of the Space Research Institution of the Northwest University. To show you a picture of how the cosmic ray detector actually looks like, it's a 4 meter, approximately 40 tons of lead and beryllium fluoride that detects the cosmic rays that brings it down to speeds that can be observed. Then also, if you look at the Hermanus neutron monitor observations and plot that against sunspot activity, we see a perfect modulation of the neutrons with a sunspot cycle. When the sun's magnetic field is quite large, that is during solar maximum, we observe the minimum of neutrons. That is to be expected because the particles, the cosmic rays are deflected away, and fewer of them are actually allowed to penetrate into the Earth's atmosphere. And so we see quite a cyclic pattern of modulated neutrons as we detect it at Hermanus, and similarly around the globe at other neutron monitors. At Sinai, there's another very important neutron monitor run by the Potchefstroom group, the Northwest University. This is how the setup looks like. We see that the cutoff of energetic particles is 0.8 GeV. That means all energies above 0.8 can be detected. And that is due to the configuration of the Earth's magnetic fields in the poles. In the case of Hermanus, it is 4.5 GeV, meaning that only particles above 4.5 GeV can be detected at Hermanus. And that is due to the inclination of the Earth's magnetic field. So in a true sense, the Earth's magnetic field actually acts as a spectrometer for allowing certain energetic particles into its environment as the strength of the magnetic field actually varies around the globe. Something that is not well known for the general public is that Hermanus has the honor of being the longest continuous operating neutron monitor in the world, just by 1 month in 1957. Although several neutron monitors were installed before 1957 or before the date, they do not qualify for this particular honor because they have been operating intermittently, and Hermanus is the one that actually has the record for the oldest or the continuous running observatory or neutron monitor in the world. Cosmic rays are also used on various applications. For instance, one of the secondary products of cosmic ray interaction into the Earth's atmosphere is the creation or forming of radioactive nuclides, of which carbon-14 is one of the most prominent ones. It has got a half-life of approximately 5,700 years. And it's taken up in the atmosphere, forming molecular bindings with carbon dioxide, absorbed by trees, coming into the food cycle, and then also can be analyzed through tree ring analysis. That allows us, if you have an old tree, for instance, of 1,000 years or so, one can easily work back what was the conditions of the sun at that particular stage, which we cannot do with the direct sun observations because these sun observations did not exist. Then, of course, beryllium-10 is another radionuclide that we normally observe in ice cores in Antarctica or in the Northern Hemisphere. It's got a half-life of close to 1.3 million years, so we can really use this to date back several thousands and millions of years to see what was the sun's behavior at a particular moment in time. And with that, we can actually detect the 11 years normal solar cycle, the 22-year magnetic cycle, then longer term cycles, 80 to 100-year Gleisberg cycle, and then also the 200-year de Vries cycle can be detected by analyzing ice cores and also carbon-14 remnants in tree ring sites. Another aspect of cosmic rays that is very important and that's shrouded in mystery is the existence of very high energetic cosmic rays. So what do they teach us about the nature of the universe? Several things, I think. Mystery of the universe, cosmic rays, there are energies above 10 to the 18 electron volt, and they are referred to as ultra-high energy cosmic rays. So there are basically three main questions concerning these ultra-high cosmic rays. How are they accelerated to such extreme energies? That is what we don't know. We don't know how the physics and the physical phenomena behind it. Where do these cosmic rays come from? And what is the composition of these ultra-high cosmic rays? These are burning questions that are screaming for an answer nowadays, and we still don't know. Well, possible sources of these ultra-high cosmic rays can be supernovas, supernova remnants. We have a very popular one that is a source of these high-energy particles, remnant supernova remnant SN1006. And then, of course, we suspect that colliding galaxies, as seen here in the picture on the left-hand side of your screen, galaxy NGC 4038 and 4039, is a high quality possible candidate for accelerating high-energy cosmic rays. Then, of course, there are other particles that are chargeless and to a large extent also mostly massless. We don't know, maybe they exist with a few, they do have mass, but the early indications were that they didn't have mass. That is the neutrinos that we observe. There's a very prominent and very important neutrino observatory in Antarctica, close to the Amundsen-Scott station. These neutrinos are fundamental particles. They are key to exploring high energy universe. As we sit here listening to this presentation, several million of these particles have already flown through our bodies. Because they're massless and chargeless, they don't induce radiation and we do not see their effect at all. But these neutral particles we think are generated in cataclysmic cosmic events. They travel for several thousands of light years, unperturbed, undeflected, and unhindered. And at the moment, the results coming from this observatory in Antarctica is revealing, or we see fundamental contributions to our knowledge of how the universe actually functions and also for physics. So I hope I've given you a little bit of a flavor of what entails cosmic ray research. The sheer existence of these high energy particles or cosmic rays tells us that our understanding of the universe is still woefully incomplete. And on this note, this bombshell, thank you very much for listening.
Thanks very much, Pieter. I've got a question. If anybody else wants to ask a question, just you can use your space bar to unmute temporarily and just ask the question. Can I go ahead?
Yes, sure. I hope I can answer.
Yeah, on one of your graphs with the quantity and energies of the cosmic rays, I think you showed the low energy cosmic rays were much more and almost in a straight line relationship to the high energy. I would assume that a high energy cosmic ray would be able to penetrate much further in the universe, you know, because it's got more energy, less easily absorbed. Would that be logical?
No, the reason why we see the only a few high energy particles, they are very difficult to detect in the first place, and their density is also very low. So we only see very few of them. And the more lower energy particles or cosmic rays have more, less energy, but they are more abundant. So that is why they are higher up in the curve. so to speak. And these are the ones that are actually interacting most profoundly with the, I would say, the constant elements in our atmosphere and creating the shower. So there's a cut-off between, or a trade-off between the energy and the amount of these particles in order to constitute a secondary shower of particles that we can detect on the ground by means of our neutron monitors. So the higher energy ones, they are very, very scarce, and they also are very difficult to detect and brought down to energies or retarded so that we can actually detect them with neutron monitors. I think most of them are being detected outside our atmosphere by observatories flying above the atmosphere, and that is where we can really start seeing them. So there are two ways of detecting, one on the surface of the Earth, and the other in outer space in satellites orbiting the globe. I hope that's answered your question.
Yeah, thanks. I do gather that it is logical that it be the processors would be able to produce the lower energies, much more of them, because they're easier to produce, probably.
Yes.
Yeah. Okay.
And
thanks. All very fascinating. Anybody else got a question? Go ahead and ask.
Peter, you said that cosmic rays' origin cannot be directionally determined because they actually spiral, they follow the magnetic field lines on their journey to Earth. So the origin of the very high energy, is that basically limited to extremely high energy processes in the universe?
This is our understanding at the moment, that it's limited to our very extreme and very violent events or transient events in the universe. And the other ones are coming sometimes from the sun and or nearby, I would say, explosions or things that we can actually see them. So, but it's very difficult. You cannot really point a detector towards their direction and say that is where they're coming from. I think in the only case that we can really detect cosmic rays is with the Hess telescope. They can have a directional, because the means of detection is completely different. They rely on Cherenkov radiation created by these particles in the atmosphere, and then one can start pinpointing the direction in which it was coming from. And that is only the extreme high energy gamma rays. So that is not a particle, but that is gamma ray detection, and that is what the Hess telescope is actually for. But for charged particles, it's almost impossible to determine the origin of these particles.
Another question is, when you show the diagram of the particles changing direction, are they deflected or bounced, or are they magnetically repelled? In which case, would the angle or the curvature of the deflection, would it be immediate or would it be gradual?
I think if you refer to what happens in the Earth's environment, the magnetic field of the Earth, that is instantaneous. You get spiraling along the magnetic field lines, but these particles are immediately deflected by the Earth's magnetic field. That is where we see different energies at different latitudes or strengths. And then also the sun's magnetic field play a very crucial role in the modulation of cosmic rays. And that is also instantaneous. There's no delay in it. The flux comes in, it is deflected, and very few can actually come through. So it acts as a filter, so to speak. If we talk about the cosmic rays in our solar system, or the heliosphere that is between the sun and the Earth, that is the sun's magnetic field. And then we also have the effect of the Earth's magnetic field, which is another effect on the magnetic or the magnetic properties, or using the magnetic properties of the Earth's magnetic field and the charged nature of the energetic particles coming in from outer space. But once they've come through the atmosphere and through the Earth's magnetic field, we can only rely on the stiffness or the strength of the magnetic field to limit the energies that you can detect at a certain latitude and longitude on Earth.
Thanks.
Derek? Derek, I have a question.
Go ahead, Jenny.
Sorry, can you hear me? So, sorry, go back to the slide that shows the relationship between the cosmic rays and the sunspots activity.
Yes.
I just want to, I don't really get the link, the correlation, or what they mean.
This one.
So you're saying when sunspot activity is high, the
Rays are high, yes.
Yeah, that the cosmic ray activity is low.
Low, yes, that is during solar maximum.
Yeah, so why is it lower if the activity is higher?
No, the sun's magnetic field is strong. It's stronger during solar maximum.
Right.
And that is relates to the shielding effect of the sun's magnetic field on the cosmic rays. So fewer of them can come through and interact with the Earth's atmosphere. That we see the minimum here, or all other minimums are related to the maximum of solar activity, and that is the maximum of the magnetic field of the sun.
Oh, that makes sense. Thank you. Now I understand.
Okay, good.
You showed a diagram earlier where some elements in the universe, like lithium and are less than others. Now, what is the relation between the issue of those elements and the cosmic ray that you were discussing about? I don't understand the link between the two.
The sources of these cosmic rays can be detected from outside or coming from the sun. There's a means of distinguishing between what is coming from the sun and what is coming from extragalactic or other galactic places. And that what we see from the sun is actually far less than what we see from other sources. And that means for those elements, those light elements, lithium, beryllium, and boron, we do not understand why it is so low in comparison to galactic cosmic rays. And we don't understand that while it for other elements, it's almost exactly the same. But for those elements, why is it different? And that is why we don't understand it. It is an open question that we cannot answer at the moment, and why it is only for those few elements, why it is only the light elements. It can only be that it must be related to a process taking place in the sun that is not the same that takes place in the rest of the universe or in other places where the galactic cosmic rays are being generated or formed.
Okay, but what I still don't understand, the cosmic rays are not molecules. They're neutrons and so on. Is that correct? So what is the relation between the elements that you detect, or don't detect, and the neutron particles?
No, the cosmic rays are not only protons and electrons, there's also other elements as well. It's a whole suite of, or basket of elements that comes from outer space.
I see, including molecules.
It's only atoms, I would say, not really molecules. It's atoms that we actually recognize.
Okay, now I understand. Okay, thank you.
Yes, okay, right.
Pieter, just on that same thing, how does one distinguish whether a cosmic ray has come from the sun or the rest of the galaxy or universe?
That is done by measurements in outer space close to the sun, and then also further back or further out, where we have satellites orbiting and measuring these, doing these measurements. So they can distinguish between what is coming from the sun and what is coming from, say, a supernova.
Can I ask another question? You posed a few questions that we don't understand. But now, apart from measuring and logging all the details of the rays that come in, what is the focus of research in this field? What are you trying to detect as a priority?
As a priority, we want to detect how are these particles actually accelerated, what is their source, what is the release, what is the release mechanism inside supernovae and pulsars that give rise to these particles or atoms that we see, and what does that help us in understanding the evolution of stars?
Thank you.
Any other questions?
Hermanus being one of the areas that has the longest history, have you made some spectacular breakthroughs and discoveries here in Hermanus?
I've recently published a paper on using Hermanus data, Hermanus cosmic rays, and doing an analysis of the periodicity in cosmic rays that has never been done before, and which shows that the orientation of the sun's magnetic field, whether it's upwards or downwards, because we know the sun's magnetic field flip polarity every 22 years, and that has a profound influence on particularly the galactic cosmic rays that we observe here in Hermanus itself. That's a mouthful, but anyway, that is one of the breakthroughs and new knowledge that was detected in using the data from this facility.
And can these rays be detrimental to human beings?
No, not at all. They can only be detrimental to you the higher you go up above the Earth's surface. And that is, as I said in a previous presentation of mine, for those people who like to accumulate Voyager miles, they fly at an altitude where these cosmic rays or the neutrons are actually can pose a danger to your health if you want to, particularly if you fly over the polar region, because the shielding effect of the magnetic field is not as good or as effective as you would fly, for instance, between Johannesburg and London, where the magnetic field does the shielding. But for people who fly through the South Atlantic anomaly region, that is where the Van Allen radiation belts come to very low altitudes into the atmosphere. And during a magnetic storm, it can have an effect in the long run. So all these pilots that they fly intercontinental flights, particularly over the polar region, they are registered as radiation workers. So they carry radiation monitors with them in order to check their health status. And when they get too high a dose, then these people are taken out of action for a while. So it can have an effect on your normal health, but here at the sea level, I think it's minuscule and negligibly small.
So astronauts are in danger too?
Yes, that's why I am personally skeptical about a flight for human beings to Mars, because then you will be completely exposed to extreme doses of ionizing radiation, neutrons, that even during a magnetic storm or an eruption on the sun, it can be detrimental. I think it was Apollo 14 or one of those missions that just by the skin of their teeth, they escaped a magnetic eruption or a solar mass ejection. And within time, they came back. And at that stage, nobody actually knew about the existence of these solar eruptions. And if they had encountered it in mid-space, that could have led to serious health risks for them as well. So even in the International Space Station that orbits around 300 to approximately 400 kilometers above the Earth's surface, they have to take precautionary measures during high levels of activity of the sun and shield themselves in areas that are designed for shielding themselves from high energy radiation. So there is a risk for astronauts flying or orbiting the Earth, and particularly if they want to go to Mars, that will require more than just lead shielding to protect their lives.
Sorry, may I ask one more question? Coming back to the various atoms that you talked about, the heavier the atoms, of course, the more energy they need to be accelerated to these high speeds. And do you find a speed difference between lighter and lower atoms?
I don't think our resolution is at the moment that much that we can distinguish. It's a broad spectrum that we see. These particles are not just monoenergetic. They have a complete range of inner particles which can span from, even if their masses are different, they span the same energy range. And there's hardly any difference in the whole spectrum of energies that you detect, for instance, for oxygen or for nitrogen, or whatever element you might choose, that you find that maybe there's less energy, less particles or higher energies with a higher mass. But all in all, if you average out, it turns out that the spectrum looks more or less the same.
Another, is lead the best? Does it slow the particles down, or does it shield them?
Just repeat your question. I couldn't catch it.
Is lead the best way to slow particles down, or why specifically lead, or does it shield?
That is the one that we know is very effective, but you can also use other composite materials that will also slow down particles. But all in all, mass and weight counts extremely heavy in outer space, and you want to limit the mass or the weight of your spacecraft, because it requires fuel, and that is a whole chain effect in all of the shielding. So that basically makes it extremely.
I was just talking about shielding on Earth. No lead.
Oh yes,
what about mercury?
No, I'm not aware of that has got a shielding effect, as it's not being used because mercury is very poisonous. So you don't want to use that in everyday life. But lead you can put in, and it's easily manageable.
Yeah,
use that.
Available. Yeah. Lovely. Thanks very much.
Yep.
Have any satellites been deployed specifically to study these particles?
There's one satellite that I know of, and that is the ACE satellite. It sits at the L1 libration point, and it is designed and equipped with instrumentation, particularly to study galactic cosmic rays. And it is delivering the results now for close to 10 years. And that is the one that I have first-hand knowledge of myself for looking at data from, say, for instance, light elements, carbon, nitrogen, oxygen, iron, and looking at the energy spread. That is why I can say that I've seen this myself and looked at it, and it reveals that the spread of energies are more or less the same around all these particles. But the A satellite is the one that is exclusively designed for particle detection.
And even this satellite has not been able to determine directivity and correlate it between a burst of particles and some cosmic event.
No, it's very difficult to do that.
Even outside the magnetic field of the Earth.
Yeah, when it was designed and built, it had equipment or technology that is not available at that time. But I think nowadays one can do that. As technology develops and become more sophisticated, it leads to much better resolution and much better utilization of your apparatus at what is at your disposal.
There was a question from Mick Finn. Do you want to verbalize it, Mick?
You can just, it's written there. Just if you just read it for me, it'll be fine. Thanks, Pierre.
Did you see that, Peter? Mick
No,
said,
I don't know where to find it.
What effect is anticipated on cosmic radiation on Earth when the Earth's magnetic field flips?
Yes, that is a very interesting question, because when the Earth's magnetic field flips or changes polarity, we anticipate that the strength of the magnetic field would be roughly 10% of its value that we have at the moment. So that means that high energy particles will penetrate very low into the atmosphere. And what is calculated or anticipated is that people will be exposed to higher doses of radiation even at sea level or at ground level. But our findings so far and what we have seen so far is that no mass extinctions actually occurred during polar reversals in the past. The last one was 780,000 years ago, and it never led to any known mutations or DNS or DNA changes in the living animals at that stage in time. So what we do know is, and according to simulations, is that roughly 100,000 people or more people will die from radiation than at the present moment, which is not of epidemic proportions, but it is still something that needs to be taken into account during that time. So I personally don't think the people on Earth will be extinguished during a polar reversal, but for sure we will definitely see far more radiation-induced cancers and effects on people with sensitive skins.
Thank you, Pierre.
Any more questions? Well, in that case, I would like to thank Pieter on behalf of the Hermanus Astronomy Center members for an interesting, very interesting talk, an enjoyable talk. It's always enjoyable to listen to an expert explaining quite a complex topic very interestingly, very lucidly, and very understandably. I think that's why is one of the reasons why he's very popular as an expert interviewee on RSG. About a fortnight ago, when phosgene was discovered in the atmosphere of Venus, the next morning, RSG had an interview with Pieter, which I was fortunate to listen to. Pieter, thank you very much. All your talks are always very memorable, and tonight's one was no exception. Thanks for the trouble, and it was most enjoyable.
Thank you, Pierre. I appreciate it. It was a real pleasure to talk to you.
Good night, everyone. Have a good evening.
Thank you. Good night.
Good morning, everyone. Thanks, Peter. It was great.
Thank you very much.
Thanks.
Thank you.
Thank you.
Thank you.
Okay, I'm going to shut down the session now, Peter. Thanks very much.
Excellent. No problem. I leave them.